So here we have a Pixel Chi tablet reference design. So this is it. This is an Intel Atom based.
Yes. And so it's with a capacitive touch, and it's a tablet, and you can turn the backlight off or on. They put a Chi button in for us.
Nice. Can you check this button? There's a button there. It's a nice switch.
Yeah.
Cool. And so actually, when you turn off the backlight, you're demonstrating over here the watts.
Yes. So here's a system with this is a wacom. This is a pen-based digitizer, and we can turn the backlight off. But first, we have a kilowatt in there that's between 6 and 7 watts, and then we turn off the backlight. Very readable.
Yeah.
And it goes down to 4 watts. That's the system that happens to be in it. There are lower power motherboard systems down to 1 watt. And if you really think about it, like the iPad, I think the motherboard takes about a half a watt, and the screen is 3 to 4 watts. And so really, if you want to reduce the power consumption of something, you've got to think about reducing the power of the screen. And the best way to do that is to turn off the backlight. So we made screens where you can turn off the backlight like this. And the plus is that they're sunlight readable, as we talked about yesterday.
That's cool. And over here, you're also showing a combination of capacitive and wide view.
Yeah, right. So I think we showed you yesterday wide view and capacitive separately, and here they're combined together with an anti-reflection coating on the top of it. Oh, yeah, here I can just scroll down. So here's an example of that together. So it works on wide view, and here you can actually see, here it's a little yellowish on that side, on the capacitive.
Yeah.
So this is wide view, right, this one. This is capacitive.
Yeah.
Here we can do double finger. And then this is those two combined together with anti-reflection coating on the top. So we can do all of those.
Nice. And so the wide view technology is something it's available.
It's available. We're sampling it now and bringing it into mass production very rapidly. I was just talking to our suppliers on that, and they can, with an order, get it shipping within 30 days. So
nice. And there's one more prototype right here. Is it a prototype or?
Yeah, this is another tablet that we're working on with AccuC, and here, it's pen-based or touch-based. It's some cool technology, and of course you can turn off the backlight. Except I don't think I got the instruction manual yet on how to turn off the backlight.
You have a switch?
Well, there's one switch on it. Let's just go ahead and throw it. Oh, it works. Okay. So this is, of course, sunlight readable.
Let's try to plug it off. Just go over the closer to the sun.
Okay, great.
And here you have it.
Here's
Just
the sun. We could take it outside and look at it in the sun if you like, but.
So does this one have the wide angle or the wide view?
This is still the narrow angle, so we can put the wide view in here. And we lost the stylus, but. And we can turn it back on. I think you can see. No, it's pretty bright, the sun on this. So there's a better way to couple. We've been we're learning a lot about how to couple the touch panels with our screens, because most LCDs aren't reflective, so you really have to match each and every layer of the screen.
All right, so is it also the anti-glare is not on this one?
This doesn't have the anti-glare. This is the sort of glass type, which is more like a certain tablet that's very popular right now.
Oh yeah. They also have the glass type where you see yourself sometimes.
Yeah, so we prefer the anti-glare type, and it's possible we can modify that for mass production on this. Again, this is Computex is sort of the coming out party for the laptops and tablets and so forth that will be on sale for Christmas this year. So we have a little while.
There was also one more company showing Pixel Chi here. It's Universal.
Yes, Universal took their tablet away.
Okay.
But here's a sign of it. Yeah. This will be back soon. Sorry, they needed an extra one for a very important customer, so they borrowed ours.
Even Google Chrome.
Yeah, Google Chrome, Windows, Android, Linux, capacitive touch, Wi-Fi and 3G, and our screen. So, sorry, that will be back in a couple of hours. But they have
Yeah.
many customers for it, which is great. So
Yeah.
we want to support that.
Okay. Thanks. Could I just ask you about the screen?
Yes. So this is our screen. This is sort of the guts of our screen. This is what we do. This is a Pixel Chi. This is an early prototype Pixel Chi screen, and this is what is in a screen, right? So we've got basically we design every layer on the substrate, every mask, the metal masks, the oxide, and so forth, the liquid crystals that go inside of it. The layers in the optical film, so the layers in the backlight. There's an LED light bar right here that couples. I mean, the way it actually works is there's a light guide plate in here where we take. This is just normal LCD. You take the light, it goes this way, and then it reflects up through these optical layers and into this LCD that we designed. And the LCD we design to be most of each pixel is covered almost entirely
Yeah.
with a mirror, and so we convinced the manufacturer to let us use an extra metal layer. Just like in CMOS, there's you can do a 3 metal or 4 metal layer process. Well, standard TFT LCD is a 2 metal layer process. We add a 3rd metal layer, and we put that metal entirely over the pixel to make it opaque. So the backlight can't get through, theoretically. But we put a tiny little pinhole in each pixel to let the light through from behind. Now, ordinarily, if you just designed it straightforwardly, you could get very little of the light through that pinhole to the front. But because of how we've designed each of the other metal layers, the oxide layer, the amorphous silicon layer, the liquid crystal layer, the color filter layers, the polarizer and retarder layers, the optical film layers, we're able to squeeze all of the light through that little pinhole to get the normal optical efficiency of a normal LCD. Basically almost the same power consumption. But the mirror makes that pixel pretty much almost entirely reflective. So that's why it looks like an electrophoretic display when you turn off the backlight. But you've got video and color and so forth, color with the backlight on, all with the cost structure of standard LCD. So that's the sort of trick, is figuring out how we could make something that we could put into mass production quickly without creating our own multi-billion-dollar fab. And so the thing that we have to do is understand how normal LCDs are made, get access to the fab. I mean, no one else has been able to get access to the factories to design their masks using the process and design rules of standard TFT LCD so they can get into mass production quickly. So this is basically like a really big ASIC. It really is. It's amorphous silicon. It's not single crystalline silicon. So
Nice.
that's what we do.
So the little pinhole you were talking about, there's one for each pixel, or?
Yeah, there's one for each pixel.
Yeah.
And we either put a red color filter over it, a green color filter, or a blue color filter. But as a result, it's triple the resolution in black and white, which is really important for text, because you usually don't read lime green text on red, right?
Nice.
You usually read black on white, or close to black and close to white. Maybe you read brown on cream or something.
Right.
But they're mostly
Yeah.
luminance channel, not chrominance channel. They're mostly black and white. And in fact, the way we see 3 or 4 times the resolution in black and white compared to color. And as I was talking about yesterday with you, MPEG and JPEG and NTSC and PAL and CCAM, everybody that encodes information does it this way, right? 3 or 4 times the black and white information
Okay.
compared to the color information. So our panels take advantage of that as well, in addition to really reflective and really transmissive and, you know.
So to reach, why not maybe reaching the same as electrophoretic in the white mode, or what you call it? Would you be able to reach that, like what you call it, the e-ink quality?
The e-ink kind of reflectance, I think these are close to the electrophoretic type reflectance. We think that we can bring that further. We can probably double that reflectance over the next few years. We believe we can do that. But on power consumption, we're already very competitive with the, if you really look at it, say a Kindle,
Yeah.
5.6 watt-hour battery, rated for 7,500 page turns.
Yeah.
So you can do the math. If you add in one more factor, how fast do people read? In English, the average reading speed is about 300 words per minute.
Yeah.
And on a 6-inch Kindle screen, it holds about 125 words. Let's call it 150 to make the math easy. So 2 page turns a minute, 7,500 page turns. That's about 50 hours. 50 hours, 5.6 watt-hour battery. That's an average power consumption of 100 milliwatts for the system.
Yeah.
That's not very good. People think electrophoretic is 0 watt, but what they're not remembering is it's plus or minus like 20 volts to erase the screen and then write it again.
Okay.
And so actually LCD is, sorry to say it, lower power consumption if you're actually using it. If it's a tag in a store to sell some vegetables, that could be a different story. But even us, we believe we can get to bistable liquid crystal if you want a sort of a frozen image, if you want to load it up and freeze the image on it. So we have a very rich roadmap. But the big thing we had to do at Pixel Chi first, the first step, the first couple of years, is get access to the fabs, because no one's done that before. It's a bit like designing a car, the same thing. Like we've designed a new car, and Toyota lets us make it in their factory. Can you imagine? It's like that. That's what we've done, is we've convinced the big LCD fabs to let us use their factories as fabs.
Cool.
Now, the next sort of phase of Pixel Chi, we can continue to innovate using their processes and manufacturing know-how and our design know-how.
Super nice.
Vision.
So now I'll go over to Universal and check out their Android, Chrome, and all that. Cool.
Okay,
Thanks a
great.
lot. Thanks.
Thanks a lot.